In the video series on Ohm's Law, you learned about voltage drop as it applies to series and parallel circuits. In those videos, we explored voltage drop as it applies to load resistance. To put it another way, the resistance of equipment doing useful work, such as lights, motors, heating elements, TVs, radios, electric power tools, etc. In this video, we will discuss another kind of voltage drop, a parasitic form that does not do useful work but steals voltage and power from the devices that do. It is a voltage drop that occurs due to the resistance of the wires that feed a load. There are 4 voltage drop formulas that apply to this kind of voltage drop, and we will explore these the 4 voltage drop formulas, how and when to use them, how to calculate the voltage drop load center point distance formula, and finally the National Electrical Code NFPA 70 code requirements as it applies. Here are the 4 formulas. The first formula is, number 1, is a single phase voltage drop that we use when we're giving the wire size. It is voltage drop VD equals 2 times R times L times I over 1,000. There's a 3-phase form for the same thing when we're giving the wire size. It's VD equals the square root of 3 times R times L times I over 1,000. The only difference between these two is that we're multiplying by 2 here and we're multiplying by the square root of 3 here. There's another one, and this is formulas 3 and 4. This is voltage drop, which is 2 times K times L times I over CMA, circular mil area. We use this when we're given K and CMA on an exam, or we calculate K. The 3-phase form is the same thing. The only thing is we're multiplying by the square root of 3 instead of 2, so it's square root of 3 times K times L times I over CMA. Again, we use this when we're given K and CMA. The first formula, single phase, when we're given wire size, is VD equals 2 times R times L times I over 1,000. In the formula above, R is the resistance for 1,000 feet of a given wire. It's found in Chapter 9, Table 8 of the National Electrical Code. L is the length of the conductor one way. If it's a cable and it's running out 100 feet, the length of one conductor is going out, but we're also coming back. I is the amperage of the load. The multiplier is 2 because the conductor goes out to the load and returns. We divide by 1,000 because the table resistance is per 1,000 feet, and we need to find per foot and then multiply by the length. Here's an example, a drawing of the wire that we just discussed. It's a single phase circuit. It has a number 12 wire solid. This is uncoated, by the way. It's 100 feet out to the load, 16 amp load. That's what it's drawing on current, and it's a 240 volt circuit. If we turn in Chapter 9, Table 8 into the National Electrical Code, NFPA 70, this is just a reduced table of that. We have our conductor sizes over here, which is, we're looking at a 12 wire. Our circular mils is 6530. This quantity where it says 1 and 7, could be a higher number later on. 1 means a solid wire. 7 or any number other than 1 means a stranded conductor. In this case, we have a solid wire. We're looking at copper, and we want uncoated. A coated wire is not an insulated wire. A coated wire is a wire that's been tinned, such as the old RH wire. We have 1.93 ohms per 1,000 feet. You'll notice up here it says the DC resistance is at 75 degrees C. That's the table temperature, which is 167 degrees F. So looking at this, here's our formula again, formula number 1, 2 times R from Chapter 9, Table 8, times L times I over 1,000. We're going to substitute the values that we know. 2 times 1.93, that's the table resistance for that number 12 wire, uncoated, solid. We have 100 feet times 16 amps, we get 6.176 volts. We take the 240 volt supply and we subtract that 6.176 volts, and we will get 233.824 volts at the load. We dropped that 6 volts just in the resistance of the wire. This is a three-phase version. You can see L1, L2, L3. We have 3 phases going out to a load. Same formula, except we're using the square root of 3. And we have square root of 3 times R times L times I over 1,000. I is current. Square root of 3 times 1.93 ohms times 100 feet times 16 amps divided by 1,000. Our voltage drop is 5.349 volts. We subtract that from the 240 and we would have 234.65 volts, 651 volts at the load. The permitted voltage drop is defined as information notes in the following National Electric Code, NFPA 70. 210.19a, information note 4. 215.2a1b, information note 2. 310.15a1, information note 1. 647.4d, 647.4d1, and 647.4d2 information note. These are all the articles that will discuss the permitted voltage drop. The information notes, they don't carry the weight of code. They're a suggestion, but they're a very strong suggestion. Here's a representation of going out to a load for permitted voltage drop. We have a main panel. Here's its circuit breaker. We have a 5% supply, 5% of the supply voltage plus the branch. We're allowed total 5% on the feeder plus the branch for a voltage drop at the load. On the branch, we're permitted 3% maximum, but combined, it can't be more than 5%. So if we multiply this out, 3% of 120 volts, we get 3.6 volts. With the 5% total on that, we have 6 volts maximum voltage drop permitted. At 208 volt supply, 6.2 volts, 6.24 volts, which is 3% of the 208, and we have 5% of that 208 volts, 10.4 volts. 240 volts, 7.2 volts, and 12 volts. 277 volts, 8.31 volts, and 13.8 volts. And finally, 480 is 14.40 volts and 24 volts. If your voltages are different than this, you would take 3% of the supply voltage. The following table represents information given and calculated in slides number 4, 6, 7, and 8. There's that number 12 solid uncoated conductor. The table resistance was 1.93 ohms per 1,000 feet. Our length was 100 feet. Our supply volts were 240 volts, and our load amps was 16. For the single phase, slides 4 and 6, our permitted voltage drop was 7.2 volts. We only dropped 6.176 volts, so we're well within the permitted limits. On 3-phase, 7.2 volts is permitted, and we were at 5.34. Again, we're under the permitted voltage drop. This is formulas 3 and 4 from slide 2. This is where we're using K and CMA. This is 2 times K times L times I over CMA. We use this when we're given CMA. In the 3-phase is the same thing, only we're using the square root of 3 instead of 2. Square root of 3 times K times the length times the current divided by the circular mill area, CMA. Again, we use this when given a K and CMA. If the value for K is not known, you can use an approximate K, which is 12.9 ohms for copper. We will use this information in the formula. 2 times K times L times I. Circular mill area for a number 12 solid wire is 6530. We got that from that Chapter 9, Table 8 of the National Electrical Code. Partial table was provided previously that we went over. And here we have, using 6530 CMA 12.9 approximate K, 100 feet, 16 amps. We have 2 times 12.9 times 100 feet times 16 amps divided by 6530 CMA, and that equals 6.321 voltage drop. If we take 240 and we subtract that from the 240, we will get 233.678 volts at the load. Approximate K provides a slightly different value than that calculated by Formula 1, which was 6.176 volts. If we use an exact K, we will get the same exact values. CMA times table resistance. This is a formula for computing exact K. We take the CMA value, circular mill area, from Chapter 9, Table 8 of the National Electrical Code. We multiply it by the table resistance for that wire, divide by 1,000, and we will have exact K. Exact K equals then 6530 for that number, that's a circular mill area for a number 12 wire solid, times 1.93 ohms for that same wire, divided by 1,000 equals 12.6029. We will use Formula 3 with exact K on the next slide. This we have 2 times 12.6029 ohms, that's exact K, times 100 feet, times 16 amps, divided by the circular mill area, 6530, we get 6.176 volt drop. That's exactly the same result that we achieved with Formula 1. If we use exact K for the three-phase formula, square root of 3 times 12.6029 ohms times 100 feet times 16 amps divided by the circular mill area of 6530, we would have 5.349 volt drop. That's exactly the same result we achieved in Formula 2. There is a separate exact K for each wire size. Stranding type, coated or uncoated conductor, as each of these have a different resistance in ohms per 1,000 feet. The resistance values provided so far are based on table resistance of 1.93 ohms per 1,000 feet at an ambient temperature of 75 degrees C. That's the temperature that was calculated for that table that we looked at in Chapter 9, Table 8 of the National Electrical Code. If we have a different ambient temperature that the wire is running through, we need to adjust for this temperature change. The formula for temperature change adjustment is given as follows. It looks complicated, but I'm going to show you how easy it is to do. R2, that's the new resistance at temperature change, equals R1, which is the table resistance value in ohms, and parentheses 1 plus alpha, parentheses T2, that's a change in temperature, minus 75 degrees C, which happens to be the table temperature. T2 is the ambient temperature. R1 is the table resistance from Chapter 9, Table 8, NEC 70. R2 is a new calculated resistance at temperature. And alpha is a constant that we use for adjusting for temperature change. For copper, it is 0.00323. For aluminum, it is 0.00330. We're going to look at just copper. The formula for temperature adjustment is given. Let's assume that we have the same circuit. Number 12, solid copper uncoated, 100 feet in length, single phase, 240 volts, 16 amp load, and we're running it through a 60 degrees C ambient temperature. And there's our formula, and we'll show it again in the next slide. So here we have R2 equals R1, parentheses, 1 plus alpha, parentheses, T2, minus 75 degrees C, parentheses, parentheses. Always do the inside brackets first and work your way out following the order of operation. PEMDAS, parentheses first, inside parentheses, work your way out to clear these outside parentheses, and finally multiply by this R1 value. So R2, this is what we want to calculate, equals 1.93 ohms, which is R1, 1 plus alpha for copper is 0.00323 times, in parentheses, 60 degrees C minus 75 degrees C. We're going to start with the inside parentheses first. 60 minus 75, you're going to get a negative 15. So we have R2 equals 1.93, 1 plus, parentheses, 1 plus 0.00323 times negative 15. Once you have a number in your calculator, leave it there. We have this negative 15, order of operations, multiplication before addition or subtraction. So we're going to multiply that negative 15, which is in your calculator, by 0.00323. And we're going to get a value in the parentheses of negative 0.04845. That's when we multiply this. Now all we need to do is just say plus 1. When we do that in the parentheses, we cleared one set of parentheses. We have 0.95155, and that's going to be multiplied by this 1.93. When we multiply it, we will get R2 equals 1.84 ohms per thousand feet, which is less than the table resistance of 1.93. So now let's put this into our equation. We have 2 times R2, not R1, times L times I over 1,000. VD equals 2 times, here's our calculated resistance for temperature change, 2 times 1.84 ohms times 100 feet times 16 amps, that's our load amperage, divided by 1,000 equals 5.888 volts. 240 minus 5.888 equals 234.112 volts at the load. The voltage drop is less than the 6.176 volts because the wire resistance is lower at temperature, less than 75 degrees C, and that means that we will have less of a voltage drop. We're going to calculate the new resistance at the temperature change. This is step 1. Calculate the new resistance at the ambient temperature. We did this for 60 degrees C and determined it was 1.84 ohms. Step 2. Use the new resistance in the exact K formula. Now we're using a different formula. We have CMA times R2. That's that adjusted ohms value, resistance value, divided by 1,000 is going to give us an exact K. So we have 6530 times 1.84 ohms. This is the CMA, circular mill area. And then that divided by 1,000 will give us 12.0152 ohms. Use the K and CMA formula now. 2 times 12.0152, which we calculated right here, times 100 feet, times 16 amps, divided by 6530, and we come up with that same 5.888 volt drop. Use K and CMA voltage drop formula. 2 times exact K at temperature times L times I over CMA equals a voltage drop Again, this is just reiterating when we put it in, we got the 5.888 volts drop. The 5.888 volt drop compares exactly to values calculated in slide 22. All the previous formulas, including exact K or approximations, the NEC does not require the following actual calculations. They are given here only for engineering purposes. Let's consider our same number 12 solid wire, 100 feet going out to the load with a 16 amp load and a 240 volt supply. It is important to note that the 100-foot cable to the load has two conductors out and back, which acts as two resistors in series with the load. Let's calculate the resistance values for each of these conductors out and back. They act as resistors in series with the load. Number 12 wire solid has a resistance of 1.93 ohms per 1,000 feet, and we have 100 feet. So 1.93 ohms times 100 feet divided by 1,000 is going to give us a resistance value of 0.193 ohms for each conductor going out and back. Now let's look at the resistance value of the load load itself. 240 volts divided by 16 amps has a resistance, load resistance, of 15 ohms. This value will not change. That's fixed. That's part of the physical characteristics of whatever machine or load is being delivered by this 240 volts. The number 12 wire solid has a resistance of 1.93 ohms per 1,000 feet, and we have 100 feet. So 1.93 ohms times 100 feet divided by 1,000 again gives us a resistance for each conductor of 0.193 ohms. This is a drawing to show that circuit. This is a series circuit now. Our load, the 16 amp load, has a resistance of 15 ohms. But each wire going out and coming back is acting as a resistor in series with this load. R1, we'll call this R1, equals 0.193 ohms. It's in series with this R2, 15 ohms. In series with this R3, 0.193 ohms. This is a series circuit. Ohm's law for voltage drop series circuit. With the load connected at the source, the Ohm's law values are as follows. 240 volts, 16 amps, 15 ohms, and 3,840 watts. This is if we actually connected this load very, very close to the voltage drop. But we're connecting it 100 feet away, going through a wire that's dropping resistance. So if we look at this, here's our three resistance values. This is the wire going out, has 0.193 ohms. The load resistance is 15 ohms, that's R2. And R3 is the return wire conductor in that cable, is 0.193 ohms. This is a series circuit, so we just have to add up these values, and we get 15.39 ohms. When we divide 240 using Ohm's law formula, if you're unsure about this, go back and see the series on Ohm's law on series circuit, and you'll see that E divided by R is going to give us I. 240 divided by 15.39 ohms is going to give us 15.6 amps. This is a series circuit. The rules tell us that amperage is the same everywhere in a series circuit. So we have 15.6, 15.6, 15.6 ohms. Actually, this is, later on I'll explain that I reduce this, I round it off here, and we'll get a slightly different answer on one of the values, but we'll be able to discuss it then. Now, I times R will give us E, so 15.6 times 0.193 ohms equals 3.010 volts. That's a voltage drop for that conductor going out. On our load voltage drop, we have 15.6 times 15 ohms is going to give us 233.98 volts. And finally, we're going to have the same values here as we do for the wire going out as in the return wire, 3.01 volt drop. And our summation of our power, 15, this is E times I equal P equals E times I, is 240 times 15.6 equals 3744 watts. Here we have 15.6 times 3.010 volts, 46.96 watts. Here we have 15.6 times 233.98 volts, and we get 3,650 watt, 50.08 watts, and again 46.96 watts here equal to there. If we had our load connected directly at the power source, we would be developing 3,840 watts, which we can do a lot of work with that. But we're only getting 3,744 watts, and at the load, only 3,650 watts. We'll explain why. If we look at a comparison of all the formulas that we looked at right now, 2.193 ohms per 1,000 feet times 100 feet divided by 16, this was Formula 1, divided by 1,000, we have a 240 volt supply. Our voltage drop is 6.176, and we have at the load 233.824 volts. In an approximate K, this is where we're using 12.9 ohms, which is an approximate K. We're using K and CMA here. We're going to get a voltage drop of 6.322 volts, and we're going to get 233.678 volts at the load. But if we calculate the exact K and we use that exact K formula, 7.6029 is the exact K, times 100 times 16 times 2 over the circular mill area of 6530 for that number 12 wire, we will also get 6.176 volts, and we will have a voltage drop at the load of 233.824 volts, the same as we got in Formula 1. Temperature change. This is where we calculated our temperature change, and we used it in the formula. 2 times 1.84. Instead of the 1.93 ohms per 1,000 feet of table resistance value, we did a calculated value for temperature change and got 1.84 ohms times 100 times 16 divided by 1,000. And that's going to give us 5.888 volts, 234.112 volts at the load. And that compares with what we had in this formula here of using exact K, 2 times 12.015 times 100 times 16 divided by CMA. We also get 5.88 volts, 234.12 volts at the load. Now here, this is a voltage drop formula that we used in the Ohm's law calculations when we're in that video series. What I did here is this 0.193, that's the ohms value for 100 feet of each conductor, and there are 2 conductors. And that formula just says that it's like R1 over the total resistance times the total voltage is going to give you the voltage drop. So here, 0.193 plus 0.193 over 0.193 plus 0.193 plus 15 times the supply voltage, we get a voltage drop of 6.021 volts, and we get 233.979 volts. The reason it doesn't match this is because when I calculated this, remember I showed you that I had some rounding errors because I took that 15.6, I rounded up to 15.6 ohms. It was really 15.59 something. They would match exactly if I didn't do that rounding. A comparison of the results of the calculations using various methods reveals that there is very little difference in voltage drop, less than a half a volt difference at the load. However, even when the voltage drop is less than permitted, there is still a cost associated with the loss of watts through the conductors and the reduced wattage at the load. A review of the information from slide 29 reveals the impact on watts. We have 94 watts lost through the conductors, 96 watts lost due to reduced circuit amps. Kind of rounded off here. The total watts lost, the voltage drop, and the reduced voltage at the load are 190 watts when we add this all together. Here, this is the 240 volt supply. Here's our series circuit resistance of 1.193 ohms, 15 ohms at the load resistance, 0.193 ohms for the wire going out, total resistance of 15.39. Okay, and we divide that, 240 volts, E divided by R gives us I, 15.39. If you divide this in, it's really 15.59 something, this amperage, and the values would be slightly different down here, and they would concur with what we got in the previous slide. However, let's just look at it this way. Here's our amperage is the same everywhere in series circuit. Again, it's 3.01 volt drop. The wire going out, 233.98 volts at the load drop, and then another 3.01 volts at the return conductor. We have 3,744 watts. We're losing approximately 47 watts in just in the wire going out, and we're losing another 47 watts. This is like a 100-watt light bulb that we just put into that circuit. And then finally, at the load, we're only getting 3,650.08 watts instead of that 3,840 watts. Now let's look at the cost associated with this. We have 94 volts lost through the conductors, 96 watts lost due to the reduced circuit amps to the load resistor or to the equipment. The total watts lost through voltage drop and reduced voltage at the load are 190 watts. That's almost like a 200-watt light bulb or two 100-watt light bulbs. 190 watts times 8 hours a day times 30 days equals 45,600 watts. We divide that by 1,000 to get it into kilowatts, 45.6 kilowatts. That's what the utilities bill us in kilowatts. So 45 times 6 kilowatt hours times 24 cents per kilowatt hour for the voltage cost on Long Island equals $10.94 per month. $10.94 per month times 12 months equals $131.28 per year loss. $64 or almost $65 loss is through the conductors alone. And then another $66 is lost due to the reduced circuit amperage, because as the resistance went up, when we added in those two wire resistances, the current goes down because current is inversely proportionate to resistance and directly proportionate to voltage. I'm going to get on to another subject here in voltage drop. This is a weighted average for indoor feeder to multiple loads. This is a voltage drop load center point formula or that we're going to look at here. Let's assume that we have 180 amp, 240 volt, single phase, 3-aught THWN feeder, 0.0766 ohms per 1,000 feet. We have to the first, we have 70 feet to an 80 amp load. On that feeder, we have a 60 amp load at 100 feet, and at 130 feet, we have a 40 amp load. We take the 80 amps times the 70 feet, multiply the 80 times 70, we get 5,600 amp feet. 60 times 100 is 6,000 amp feet. And then 40 amps times 130 feet equals 5,200 amp feet. When we add up all the load, it's 180 amps. Our amp feet is 16,800. This isn't amp feet, we want to get it into feet, so we're going to divide by the 180 amps. And our load center point is 93.3333 feet. This 0.33, the threes go on forever. We could have said 93.3, put a bar over the 3. It means the same thing. We use a voltage drop load center point distance to calculate the total voltage drop to the farthest load. That's that 40 amp load. So we have 2 times 0.0766 ohms, and we get that from Chapter 9, Table 8 of the National Electric Code. For a 3-aught conductor, it's going to tell us that its resistance is 0.0766 ohms, times that center point distance, 93.3, times the total load of 180 amps divided by 1,000, gives us 2.57376 volts drop to the farthest load. We can use another method shown on the next slide to calculate the voltage drop, but it's a little more involved than using the center point one. Here we're going to start with voltage drop 3. This is to that 80 amp load. 2 times 0.0766 times 70 feet times 80 amps divided by 1,000 gives us a voltage drop of 0.85792 volts just for that 80 amp load. And here we have 0.85792 volts also. On the 60 amp load, we have the same thing. 2 times 0.0766 times 100 times 60 divided by 1,000 gives us a 0.9192 volts drop for that. If we add this 0.85792 plus the 0.9192 volts, we get 1.77712 volts drop for when we get to that 60 amp load. Finally, number 1, we have 2 times 0.0766 times 130 times 40 divided by 1,000 gives us a voltage drop just for that 40 amp of 0.9766 volts. But if we add that to the 1.77712 volts, we get a total voltage drop at the farthest load of 2.57376 volts. If we add this plus that together, 0.85792 plus 0.9192 plus 0.79664, all the individual voltage drops, we come up with a total of 2.5737 volts. The drop at the farthest load then, the total voltage drop is 2.57376 volts. We have a 240 volt supply, so that's not much of a voltage drop. The 240 volt load would have a permitted voltage drop of 7.2 volts if this was a branch circuit, but it is a feeder. If we assume the maximum 3% in the branch, then we are permitted 2% in the feeder, or 4.8 volts. We are well below the permitted value at 2.57376 volts, okay, of that 7.2 volts. But this does not mean that we can choose a smaller wire. Remember, we chose that 3/0 because if we went to chapter Article 315B16, the ampacity table in the National Electric Code, for 180 amp load, 75-degree column, it would require a 3/0 conductor. We cannot make this smaller than that because it has to carry that full 180 amp load. Some textbooks will tell you that you can reduce the conductors of the farthest loads as the amperage drops off, but in most cases this is not permitted by the National Electric Code, NFPA 70. For example, in the indoor feeder just evaluated, we had a 3-aught feeder supplying an 80 amp load at 70 feet, a 60 amp load at 100 feet, and a 40 amp load at 130 feet. These two code sections, 240.21 and 240.21b4, kind of explain, this is in the tap rules. And it tells us if the taps of a feeder are inside, you're not allowed to reduce the conductor if the conductor length, the taps are greater than 25 feet, unless it is in a high bay industrial facility, and you can also not tap off a tap. However, you can reduce the conductor sizes outside, such as when installing parking lot lights, because tap rules do not apply outside. Here's a drawing representation of this circuit that we calculated before. 240 volts single phase, 3-aught THWN feeder to 70 feet to the 180 amp load. Okay. A number 2, this is if we were reducing these conductors. A number 2 THWN 30 feet to the 100 amp load, 30 feet here, which because it's this is the 40 and the 60 gives us a 100 amp load, and the number 8 to the finally to the 40 amp load at the end. So we would be putting a number 2 conductor, 3-aught conductor here, 2-aught conductor there, and a number 8 here. However, this is not permitted on this one because 240.21b4 tells us that if it's over 25 feet, it's not an industrial high bay, we would not be allowed to make this tap with that conductor. Over here, this is even worse because the same thing, this is over 25 feet, we're not permitted, but we're also not permitted because when we tap this one off of here, the 60 amp off the 80 amp, the 3-aught conductors here, that's a tap. We're not permitted then to take a tap off a tap, so that's another violation of code. Here's a table that kind of explains everything that we just went over. Voltage at the 40 amp load. 80 amps times 70 feet equals 5,600 amp feet. 60 amps times 100 feet equals 6,000 amp feet. 40 amps times 130 feet equals 5,200 amp feet. We total these amps, we have 180 amps. We total the amp feet, we have 16,800. We divide that 16,800 amp feet divided by 180 amps. Amps cancel out, and we're left with 93.3 feet, bar 3 feet. 2 times, let's look at putting this information in our voltage drop formula. This is a single phase voltage drop formula, and we're given the wire size or the wire resistance, which is 3-aught conductor. Its resistance is 0.0766 ohms per 1,000 feet. 2 times 0.0766 ohms times 93.3 feet times 180 amps divided by 1,000 gives us a total voltage drop of 2.57376 feet voltage drop. 240 volt supply minus 2.57376 volts drops equals excuse me, 237.42624 volts at the load. At the 60 amp load, we would have 80 amps times 70 feet, 60 amps times 100. This is 5,600 amp feet, 6,000 amp feet, 11,600 amp feet, and we have 140 amps total. So 11,600 amp feet divided by 140 amps equals a 82.8571486 feet. We put this into the equation and we find that we're dropping 1.77712 volts drop. If you go back, you'll see that we actually had that number when we calculated it a slightly different way. 240 volts minus 1.77712 volt drop equals 238.22288 volts at that load. And then finally, for the 80 amp load, it's just 2 times the wire resistance, 0.0766 ohms, times 70 feet times 80 amps divided by 1,000 equals 0.85792 volt drop. 240 minus 0.85792 gives us 239.14208 volts at the load. So we would measure at the 40 amp load. If we put our meter on it, we would read 237.42624 volts. If we put our meter at the 60 amp load, we would get 238.22288 volts. And if we would measure at the 80 amp load, we would get 239.14208 volts. This concludes the instructional portion of this module. Be sure to click on the link below and take the online quiz. If you don't get a good score on it, keep going back and reviewing this video as many times as it takes until you understand all the information. Thank you, and be sure to click on all the links below. Thank you.